Welcome back, my aspiring statisticians. We are going to continue our study of 8.1 by using StatCrunch to find the confidence interval. In example 2, we knew that we had an n value of 36. We had a population standard deviation of 3 and a sample mean of 68. We were also looking for a confidence level of 90%. Well, this time, we're going to ditch the 90% and make it 95%. So we want to be even more confident in our answer. The good news is we're going to use StatCrunch for this one. So if you want to go to StatCrunch, you have the steps to follow to open those up. And when you get there, you're going to fill in 36. That is not the sample mean. 68 is your sample mean. 3 is the standard deviation. The sample size is 36. You're going to choose confidence level for mu. And our level is 0.95. When you click on compute, Desmos is very kind. It lets you know that your confidence interval is between 67.02 and 68.98. It takes a lot of the work out of the equation. If you can pull out what you know and type it into Desmos appropriately, it's a great help. If you're not sure what you're doing with Desmos or with StatCrunch, it is just the fastest way to be wrong. So pay attention to what you're doing. There's a warning down here warning you that the standard error in StatCrunch is not the same thing as the margin of error. Don't get caught up in that trap. So here we go. They've given us two pictures. One has a confidence level of 0.95. The other has a confidence level of 0.9. Notice that with the confidence level of 0.95, the interval is wider than it is with the smaller confidence level. So we're going to kind of summarize what's happening. Increasing the confidence level, just like you saw in the purple picture to the green picture, increases the error bound, making the confidence interval wider. Decreasing, so if we go from 95% to 90%, we decrease the error bound, making the confidence interval narrower. And if we change the sample size, increasing the sample size causes the error bound to decrease, making the confidence interval narrower. Meaning that the larger the sample size is, the more accurate our estimate for mu will be. Decreasing the sample size causes the error bound to increase. So in other words, if we have a small sample, our chances of getting close to mu are going to be smaller than if we have a larger sample. Decreasing sample size causes error bound to increase, That makes the confidence interval wider. So we're going to take a look at our last example. In these examples, we are given the confidence interval. And asked to find the EBM, or we might be asked to find X bar. Either one is fair game. While we're doing these, EBM sometimes just gets shortened to E. That's okay. You know, math people are inherently lazy, and if we can write things in a shorter way, we'll do it. We have two formulas that might be helpful. So here we go. Suppose we know that a confidence level or a confidence interval is 65.31 to 69.45. Well, I know right off the bat that this looks like an upper bound, just kidding, a lower bound, and then an upper bound. And we want to find the error bound. We may know the sample mean is 68, or perhaps our source only gave us the confidence interval and did not tell us the value of the sample mean. So here's what we know. We know that we have a lower bound of 65.31 and we have an upper bound of 69.45. We don't know anything else. We want to find the error bound first. Well, to find the EBM, remember the EBM is that space in there. We're going to do the upper bound minus the lower bound divided by 2. So in our case, we're going to do 69.45 minus the lower bound and divide by 2. That means our error bound, or our EBM, is 2.07. So that's the distance from our lower bound and our upper bound to the mean. Now we're going to calculate the sample mean. This time we're going to add them together and then divide by 2. So we'll add them and divide by 2, and we get 67.38. Now, could I have gone up here and taken 65.31 and added 2.07? Absolutely. Would it have worked? Absolutely. So that's another way you could do it. But what you just did was find the mean and its cushion on either side. Now we're going to look at finding sample size. The following formula is used for determining sample size needed to estimate a population mean. A researcher planning a study who wants a specified confidence level, so maybe 90%, and an error bound can use this formula to calculate the size of the sample needed for this study. So this lets that researcher know exactly how many people he needs to round up to be 95% confident in his results. Either one of these will work. You choose. For rounding, if we do these and our sample size ends up being a decimal, you're always going to round your sample size up to the next biggest whole number. So assume we want to estimate the mean IQ score for the population of statistics students. How many students must be selected? So right there, that sounds like I need to find n. If we want 95% confidence, so my confidence level is 0.95, that the sample is within 3 IQ points. So my EBM is 3 of the population mean. Use a standard deviation, and that's a population deviation, of 15. Well, I've got to go get StatCrunch because we have to find that z-score. So I'm going to split my screen. To get the z-score, I'm going to go to Stat, and I want the normal calculator. I'm going to go to Between. And the only thing I'm going to change is that last box. I want it to be 0.95. So for a 95% confidence level, my z-score is going to be 1.96. So I'm going to plug everything I have into the formula. I just found the z-score. Sigma is 15. The EBM was 3. And those brackets say to not cube, square everything. When you plug those in the calculator, you get 96.04 people. Now, I don't want 0.04 of a person. That's going to be messy. And our roundup rule said, if you have a sample size that involves a decimal, you round it up to the nearest whole number. So it looks like our researcher needs 97 people to be 95% confident that the sample mean is within 3 IQ points of the population mean. And that right there is the end of 8.1.